Hello, welcome to the wonderful world of radio frequency and electronics engineering. On the bench for repair today is a TENMA 72869A 0 to 32 volt per channel power supply with a maximum current of 3 amp per channel. We've got two power supplies on the bench today. The one on the left is apparently working fully, and the one on the right has got a defect, which we'll have to confirm shortly. These power supplies came to me fairly recently from an auction sale, and I picked both of them up fairly cheaply, so we'll be able to strip them down, have a look inside at both power supplies and see how they work, and go through the features and obviously try and find the fault and hopefully repair them. Now, the one on the left, as I say, is allegedly a fully working power supply, but we'll have to test that as well. TENMA, I believe, is a Chinese manufacturer, but they are sold through a UK outlet here in the UK called Farnell Electronic Components, which is one of the bigger suppliers, equivalent size to CPC and Element 14, etc. And I think Element 14 is part of Farnell Group, actually. And big companies like RS Radio Spares here in the UK as well, I think, sold these. So they are actually sold quite widely across the European markets, and no doubt worldwide markets for lab or benchtop power supply customers. So they're not meant to be a low-end power supply. They retail about 178 UK pounds, Great British pounds, with VAT. I think it's about 213 pounds, something like that, roughly. So you know, they're not the cheapest of power supplies, but they're sort of, I think, priced middle of the road when you compare it against something like a Rohde & Schwarz. So this is a typical example of a Rohde & Schwarz high-end power supply, which with this price point being at the many thousands of pounds for the purchase of this, you're paying for the accuracy in the voltage and current, how many parts per million accuracy this is. So this is a very accurate high-end power supply. So obviously that's the reason why you pay such a lot of money for such things like that. Okay, so this is a working power supply, so we'll just have a quick look at it, its construction and quality. Obviously on the front we've got the usual controls of voltage, variable voltage control, we've got the variable current control, mirrored on both sides because obviously it's dual channel. We've obviously got the binding posts here, the power button there on the left hand side, blanking plate, which admittedly does look very similar to this blanking plate here, where we would have the third channel binding post connected there if it was a 3-channel version, which the third channel obviously gives a fixed 5-volt output if you've got that model. We've got the track button there, so when we press that in it will then track the other power supply section, so therefore we can get more output voltage, double the output voltage by linking the positive and negative terminals of each channel together, and then the N positive negative terminals here would have as many as 64 volts DC applied depending on what you set the voltage to. So we'll have a look at the track function. Looking at the construction of it, it's very well made, it's very sturdy, very strong, good quality construction. We've got a nice rubber carry handle on the top, none of the sharp cutting sort of into your hand type carry handles that we see on so much equipment these days. Quite good quality spring loaded handle. The actual cabinet itself is again this like anodized plastic coated sort of metal, so quite good quality. There's no sharp edges on there, nothing to cut yourself. On this particular model we've got a big heatsink on the back. We've got the mains IEC with the fuse holder just in there. So the mains fuse lives inside there. Underneath we've got, there's a bit of a gap there, I must admit, just under there. You can probably just see into there. There's like a, you know, you can definitely see into there. So perhaps that could have been better, having screws here to bolt it down. But on the bottom we've got the usual plastic feet, well ventilated as well. Quite well put together really, and it's obviously China export, so it looks like as if it's Chinese. This is a linear power supply, not a switch mode power supply, so we will test it and see what voltage output accuracy it's got now. Now we've got the digital voltmeter set to DC mode already over in this side here. We'll use this as well for checking the current as well as the voltage shortly, and we'll test each channel and just verify that this power supply is indeed okay. So we'll connect the positive and negative leads up to the power supply on this channel 1 and just check that. So what we're reading, we're meant to be giving out 13.7 volts, and it's actually providing 13.82, so it's approximately 120 millivolts higher than what it should be. But let's just have a look. Let's put it to 14 volts. Oh, now it's only 40 millivolts above where it should be, because it's now reading 14.04. So let's just turn it to 13 volts precisely. That's 110 millivolts higher than it should be. At 12 volts, maybe within its accuracy. We'll have to look at the spec shortly. 12.05, it's 50 millivolts higher. So yeah, I think it's in good enough spec. That's 10 volts. So obviously we've not got the 100 millivolt resolution, well, below 100 millivolt resolution on the voltage display, because we've only got a 3-digit voltage display. So that's reading 90 millivolts higher than it should be at 10.09 volts. So that looks to be okay to me. We can now measure the current on the 10 amp scale and put it into current limit mode. So that's what we'll do next on channel 1. Okay, so we've now put the meter into the 10 amp scale current mode. We've got the output still connected here to the meter. We've got the current limit on. We've obviously turned the current limit on the power supply to minimum, so the voltage has disappeared while we obviously increase the current, so we can measure the current that's being provided. So we should be able to measure up to the 3 amps. So we'll just set it at 500 milliamps roughly, around about that, and just check the accuracy on the current meter. So yeah, pretty spot on. 497 milliamps there. So let's turn it up to 1 amp roughly and see whether that gives us an amp precisely. 1 amp. So yeah, very good, very good. And then let's try 2 amps. Just over 2 amps there. See if we can finally control it, because it is a little bit coarse. So let's just try and get that there. 2 amps. Pretty good again on the current meter. And then we'll take it up to its maximum level now, which is 3 amps. And hopefully it won't release the magic smoke. So that's good. 3 amps, 2.99 amps. And obviously if we try going higher than that, it limits, maxes out at 3.13 amp, which is what we can see on the current meter, roughly there. So it's near as damn it. So that looks good. So the current is accurate on channel 1, and so is the voltage. So that's pretty good. And obviously if we were to set, say for example, a current that we can set by shorting the output, and then we said set it at 1 amps. If we were to draw less than 1 amp, then obviously the voltage would be there. But once we effectively short the output or draw more than 1 amp, then it will obviously limit. So that's where we're at. So that just shows you how accurate that is. Okay, we'll move on to channel 2 now. Okay, so over to channel 2 now. We'll just check the voltage quickly on that, and we've obviously moved the current meter, disconnected that and put it onto volts before we do this measurement. And already we've set the power supply to 14 volts DC, and it's reading 14.1, so approximately 100 millivolts higher than where it should be. If we just turn the voltage right up to something like 20 volts or thereabouts, we can hear the relay go over there for the different taps in the transformer. We'll get to 20 volts DC, so 20.23, so approximately 230 millivolts higher and then the actual display, although you can adjust it slightly there. If you just get it to the bottom of the 20 volts limit there, it's reading 20.18, so 180 millivolts higher than where it should be. And then if we keep turning, it's like we're still in the 20 volt range there, and it's 220 millivolts higher. So there is a bit of adjustment within the actual numerical value there. So lowest we can get is 20.18 for that 20 volt accuracy. So yeah, I think that's probably within specification, and if we keep going up to 32 volts roughly, let's just double check that, seeing as we haven't measured any of the higher voltages, so just reduce that. Let's have a look. 32 volts. Yeah, there was a little bit of a sticking point on that there. You get it to its maximum and it loses its sort of control at the top end, because it's the wiper on the 10-turn pot which has sort of reached its limit, and you have to back it off a bit. 32 volts, and we've got 32.3 volts there. And then if we turn it right down to something like 10 volts and see what it's like on that, because we're obviously using a different tap on the 10 volt scale. Again, 10.1 volts roughly, and then if we get it down to like 5 volts for the next tap on the transformer, and then it's reading approximately there. If I just get it to that 5 volt thing, 5.041, it's only 40 millivolts higher than where it should be according to the meter there anyway. So that's well within accuracy. So yeah, we'll move on to the current. Right, we're ready to do a current measurement here. We've put the multimeter into the 10 amp current scale with a current shunt, and we're ready to make that measurement. Now what we'll do, we'll wind the current down to minimum so the voltage obviously disappears, because you don't want to short the power supply out at maximum current or whatever just straight away. So we'll connect the positive lead back up. Now we're ready to make a current measurement. So we'll increase the current limit to 500 milliamps again, which is on the green scale here, and we'll just double check that on the multimeter. There we are. We've got 497 milliamps, which is quite good resolution there and accuracy. If we get up to about 800 milliamps maybe, let's just check it there. Again, 794 milliamps. And then if we take it to 1 amp or 1000 milliamps, let's just see if we can get that fine adjustment there to 1 amp. We're talking 987 milliamps roughly there. If I get it to 1 amp again, it seems to drop down. There we are, 997 milliamps. Okay, then we'll take it up to 2 amps. See what current it gives there, accuracy wise. So just very finely adjust it, 1.972 amps. And then if we take it right up to, it keeps dropping down though, doesn't it there? Let's just double check that again, because the measurement wasn't quite right. So there we are, 2 amps. Yeah, 1.976 amps there, yeah. 2.5 amps. No magic smoke coming out of it yet, so that's good. So 2.463 amps. So it's quite accurate. It's not too far off. So let's get it to 3 amps then. 3 amps. 2.95 amps. And then at the maximum 3.13, it's reading 3.071 amps there. So we'll just take that back down to minimum again. So yeah, looking pretty good. We'll just check the track function now by doing the link, putting this into track mode, and then linking, I think it was a positive to negative there, and then the outer terminals become the higher voltage. So we'll just have a look at that now and see how that works, because obviously when I press the track button in there, the voltage sort of disappears on channel 2. I think it's in the instruction manual, it tracks the voltage of channel 1, but obviously it would double it. So whether that takes account, whether that changes to 20 volts when we link those two together, and then this reads a current, I believe. So we'll just check that and see how that works. So back soon. Okay, so now we're ready to do a tracking mode measurement. So earlier we were making the single mode measurement, so per channel. Now when we press this button into tracking mode, we notice the voltage disappears on this side where this is maintained. Now in the manual it says if you connect the positive output of one of the channels to the negative of the other, then the two outer posts become the higher voltage. So we've got the crock lead set up there. If we just connect that there, oh that's good, yeah, it's gone to 10 volts. And then when you adjust channel 1, it says, then it'll adjust the voltage then for both channels, which it is, it's tracking, it's doing that mode. So if I wind it up, you know, obviously the taps are going over in the transformer. So we'll put the current limit to high on both of them. Now if we go on to either these two outer terminals, we should be getting 40 volts now, because channel 1 voltage is added to channel 2, and therefore we should be getting the higher voltage. So we've got the DVM on, obviously. If I connect that in there to the negative and then to the positive, so we should be getting about 40 volts, which we are, 40 volts DC. So in theory we can get a maximum of 64 volts DC out the power supply. So if we just keep going up to 25 volts, obviously, so we should be getting 2 times 25 volts, which will then give us an output of 50 volts DC. And then if we keep going up to 30 volts, 30 volts there coming up, 60 volts, and then obviously a maximum of 32 volts, should be 64 volts DC, which we're getting. So that's the track mode taking place there. Now altering these controls doesn't do anything, so obviously that is the current limit for both channels as well on these two controls for the current. So yeah, that works. So obviously that's quite a good thing if you're wanting the higher voltages for certain experiments. At least you can get it up to 64 volts. We'll just take it through the tap, all the tap ranges on the transformer, which we can hear with the clicks of the relays. So 2 7s are 14, so yeah, that's okay. Yeah, so again 5 volts should equal 10, and it is on the multimeter. So yeah, that proves that that works, and the track function is fully working. So obviously if we remove the taps that we put in place, well, it's not getting voltage out obviously, and then we can go back to what is the single channel modes, which are separate from one another, and we can obviously adjust that, you know, depending on what we want to do. So that proves the working power supply does actually work, which is good news. At least I'll have to look at one power supply now instead of two. Right, well, we've got the covers off now, this power supply that we've been testing. This is the working power supply, obviously. A good note here about electrical safety is don't have a thing plugged into the mains when you're looking inside such a thing and touching, you know. Obviously, if you were to do that, there's a potential for you to have half a day with the undertaker. So always be careful about electrical, so make sure things are unplugged physically from the rear of the instrument, and therefore you can't make any errors. Okay, so looking inside, we can see obviously that it's a linear power supply, not a switched mode, simply because we've got the presence of a toroidal transformer here. Looking at the transformer, it seems to be well insulated, quite a large transformer. It is interesting to note that on quite a lot of power supply designs, you'll often see these transformers actually vertically mounted instead of horizontally, just for space saving. So there'll be 2 brackets coming from the chassis going up like this, and then the donut transformer on each side, and it'll be sandwiched together. In those cases, it's very important to have an insulated washer underneath the securing nut, because then you get a shorter turn through the chassis of the power supply, and obviously that causes undesirable heating effects and other problems and electrical noise, which you don't want. Obviously in this context they still employed an insulating washer under the nut, even though the top disc on the transformer isn't actually shorted to chassis. But as I say, in power supplies where we've got the brackets coming across the bottom or across the top, say from here to there, then we would have a shorter turn in effect through the chassis, where the inductance and the coupling of the transformer onto the central bolt would provide a very tiny voltage but yet an extremely high current, which would be conducted through the chassis of a power supply and causes chassis to heat up. And if anybody's ever seen one of the Weller soldering guns with the triggers, where basically if you take one of those to bits, there's actually a transformer inside, a big inductor which is connected to the mains via a switch, and then in the middle of it is a bar that comes through and then goes outside the soldering iron where your soldering bit connects into, which is essentially an electrical short circuit. And I'll show you one of those a bit later on, but basically this would be the same principle. If we had a chassis connection from here to the chassis, another piece of aluminium bolt in here, then we would have a shorter turn. So to prevent that occurrence, they use an insulating washer under the nut to prevent this bolt from having an electrical short through either side of the transformer when it's bolted to the chassis, in a horizontal format or in the vertical format even, where the tops are connected to the chassis. In this case it isn't, but it's worth noting that, particularly when designing power supplies. Looking at the architecture of a device as we go further into it, we can see on the back here we've got what appears to be the voltage regulator rectifier board. We've got two smoothing capacitors, which is surprisingly small really for a power supply of this grade in my opinion. We've got the independent diodes, which 4 diodes forming a bridge rectifier formation. That again isn't rare to see, but it is quite unusual these days because most power supply manufacturers tend to go for a bridge rectifier single package, which is bolted to the heatsink or the chassis floor to give it heat sinking and thus provide longevity, particularly if a supply is used in a test environment where it's delivering near its maximum or at least half its rated current over long periods of time. These diodes are going to get very hot, and I can't see any fan in here, anything to keep it cool, although they've taken measures to stand off the diodes from the circuit board, which they've done quite well here to get them plenty of airflow around them. There aren't actually any heat sinking on them, so potentially, I'm not saying it would happen, but there is a potential for them to desolder themselves if it gets too hot. So therefore, that's worth taking a note of. Now down here, we've got some relays, these in the blue packages, and these obviously switch in, as we heard earlier when we're testing, the different taps on the transformer in order to select the different voltage ranges. So again, the power factor is taken into consideration because we've not got a transformer with a single secondary output where it's a particularly high voltage, say 70-80 volts, and then obviously when we want 5 volts out the power supply, we've got close on 70 volts rectified supplied to the transistors, the series pass regulators, and then we're only providing 5 volts output at say 3 amps. The wattage is quite immense, and thus components heat up quite rapidly, and it can become quite inefficient with regards to its heat. So in that case, what they do is they have, when we select the lower voltage ranges, select different taps on the transformer, so we have a less voltage then applied to the series pass elements, which then reduce the power factor and thus keep temperatures down and prevent things from overheating. So when we look at the transformer here a little bit closer, you can probably see on the camera there's lots of Chinese writing on there, so it's obviously a Chinese product, but there are some indications of the primary and secondary winding voltages. So we've got here two primary coils that will be linked in series for UK supply, in this case 240 volts, but here we've got 210 volt coils for the primary, so 220 volts AC at 50 hertz, which is marked there. We've got some Chinese writing, but we've got here, it says here, I think that says 9.5 volt tap. I think we've got a 14 a 23 and a 34 volt tap. We've also got an 18 volt and an 18 volt. Again, repeat again there for the second channel, 0 to 14, 23 and 34 volts. So in essence, we've got different taps for each channel that the power supply for isolation. So we have a group of taps for one channel, which is switched by these relays, and then a second group of taps for the second channel, which is switched by these relays. So we've got the electrical isolation between channel 1, channel 2, even at the transformer side. So that's worth noting. So the transformer's quite good quality. The capacitors, I don't know, they're tiny little capacitors, those really. They're made by a company called Chang. I can just see that written on the capacitor. I think they're 3,600 microfarads, so they're quite low capacitance. But yeah, I think the capacitor's a little bit small in my liking. These are not held down with elastic, so essentially they could, vibrate off if given used in environments where there's high vibration. We've got the series pass transistors or FETs on the back. They've actually gone to two extremes here. They've bolted it to this big heatsink on the back, but also there's these little heat sinks anyway that are strapped to the transistor's tops. So on both sides of the case of the transistor, there's a heatsink applied, one to the front part of the transistor and one to the back with these insulating mats that are underneath them. The cable looms are quite tidy. They've actually fastened the cables together using some kind of lacing technique. I'm not very happy about the mains earth though, which is down here, because these two mains earth wires, one going from the IEC, the other then going to the chassis or centre tap on the transformer, is going down to the chassis via soldered connection onto a ring connector rather than a compression. Doesn't look as if I've got any shape-proof washer there or anything like that on this mains earth. From what I can see, it's only a tiny little affair. It's not really what I'd be looking for with the mains earth. We know we're talking a proper ring connector that's compression with a shape-proof washer, proper bolt down. This is actually used as the bolt for the heat sink, whereas normally there will be a separate fastener bonded to the chassis, which is just specifically for the earth connection. But hey ho, that's how it is. On the front panel here, we've got the 10-turn pot for the voltage, variable voltage control on both channels, as we can see on the other side there too. That is, again, a high quality, very costly component, especially for the number of turns. I think they're 10-turn or 20-turn pots, these. We don't have the same though for the current, because the current is just basically a wiper variable resistor which is soldered on the board under here. Now if we look at the main board at the front here, which is where the displays are and the processors, it does seem as if there's been a bit of manual soldering going on after it's been run through the solder bath. It looks like as if there's some even soldering on these display units. There's 4 display units, obviously 2 for current, 2 for voltage. We've then got the display drivers. Some of those look like as if they've been resoldered as well, perhaps manually. I don't know, but it does look like as if a bit uneven soldering on them. So perhaps for quality they've had it on after it's been through the solder bath and the components have been soldered, they've had somebody manually solder or go over the connections manually. This seems a little bit too close to the hole for the screw on the top. The screw for the case goes through the top just there, and that's actually underneath it, so there's a potential for the screw to bite into those cables and cause obviously a short. I'd have liked to have seen that tucked out the way more, but that's how it is. Yeah, so that's about it really. I think down here there's some terminals with some capacitors on them. You don't want a high level of capacitance on the output terminals, because obviously they're varying the voltage, and the capacitors will drag the voltage about, both when you're trying to turn the voltage down at very low currents. It would take some time to get to that voltage because of the capacitance on the output. So you don't really want big capacitors there. There's a couple of capacitors, one on each channel. So yeah, that looks okay. But yeah, I mean, observations, decent quality, not too bad. Could be a few improvements here or there. We've got pots here that we can calibrate the output on each channel of the power supply. The board's clearly divided into channel 1, channel 2. You can see that there's sort of a mirror design. But at least with these potentiometers, if you had a calibrated voltmeter and the power supply was slightly off, at least you can come in and adjust these potentiometers and obviously get the calibration correct. So that's pretty good. At least it allows you to adjust it. Now the capacitors do concern me a little bit, I must admit. Chang, I've never heard of Chang, obviously a Chinese make of capacitor. Don't know what the quality is going to be like on them. Yeah. I mean, when we look at capacitors in power supplies, generally, particularly high quality power supplies, then we're looking at capacitors this sort of size and value. But there are obviously advantages to using capacitors like this, simply because these capacitors are high ripple current capacitors. Capacitors which are used in this power supply, these little dinky things, they're not actually designed to handle any high level ripple current. But there again, this power supply is only designed for 3 amps, but even so at 3 amps then those capacitors may start to struggle to give limited ripple from them. But just as a bit of a sideline, these capacitors here are used in quite a lot of very high quality power supplies. There's a reason why they're so large and heavy. I mean, these are incredibly heavy, probably about half a kilo in weight. This is rated at 33,000 microfarad at 40 volts DC. But in particular, it's got high ripple current, what's called a computer grade capacitor. But it can produce up to 22.6 amps peak inverse current at 65 degrees C. Well, that's basically will translate to in between the, if we were to use a half wave rectification where we've got the positive pulses coming through every half cycle, for example, developed across this capacitor, in between those half cycles in a high current application, when we're removing from the supply a high level of current into a load, then the capacitor is the device which keeps the output regulation of the supply at minimum ripple. So naturally, between the half cycles of the mains frequency of the rectification at 50 Hertz in our case here in the UK, this capacitor is effectively filling the gap between each half cycle, and so the charge that's contained within the capacitor is being sucked out to the load, if you like, in between each half cycle. And so if we've got a capacitor that can't handle a high peak inverse current, then basically the capacitor will die quick between each half cycle, and then we would then get the sawtooth wave. So where the positive waveform comes up, as it starts to go into the cycle where there's no conduction, then the capacitor essentially is maintaining the charge, and thus then the voltage will drop off quite sharply if the peak inverse current rating of the capacitor was quite small. And so depending on the ability of the capacitor to supply the charge in between the half cycles of the rectified waveform denotes on how good the output ripple would be from this capacitor. And so it's very important when we're dealing with high current power supplies with a high regulation accuracy that we use very high quality capacitors with a very good peak inverse current rating, because what we don't want, particularly in digital circuits, when we have high ripple on the output, of course through high currents being drawn. And that's where these capacitors come in. And you'll often see on this channel, when we look at other power supplies, capacitors like this employed within them. And this is particularly important that you have such good quality capacitors, because these are the heart of the instrument when it comes to power supplies. So that's a little rundown on these little nice capacitors. Obviously, you know, quite expensive, very heavy, need a lot of space inside a power supply to get these in. So hence the reason why, you know, a lot of these lower end power supplies or with lower current capability tend to go for the smaller capacitors. They'll do, but they're not the best. So that's my stance on that matter. Okay, so this is the other power supply, which is allegedly faulty. We'll just have a quick look at it, turn it round. It is a slightly different one to the other that we're just looking at, because it doesn't have a heatsink on the back like the other one did. The other had a big black finned heatsink on the back. And if I remember rightly, the other one didn't have an international voltage selector either, which we've got on this model. Even though it's the same model number, it must be a different variant. Yeah, so very strange. Yeah, we've got two transistors here we can see clearly bolted to the back chassis of the enclosure there. There's a fan, which I can see through the grill there, just sat behind, so it's obviously blowing air, either sucking it in or blowing it out. And yeah, so very similar to the other one, and same case and everything, same part number as well on the front of the unit. So whether this was made earlier or later, I'm not quite sure yet. But let's check it out anyway and see if we can get this fault to reveal. So turn the power on. So we've obviously got the voltage there on both channels. Let's see whether we can adjust the voltage on each channel. So looks like as if that's adjusting okay so far. Take it up for its ranges. We'll hear the relay clicking in for different taps as we go through the voltage ranges. That's another click there. See if we get it up to 32 volts. Without any smoke coming out of it. So let's just see if that is possible. Yeah, we're getting up to 32 volts. That's it. Okay, so nice smooth control. No notches in it or any dodginess. That looks good. Yeah, get it right down to bare minimum. There we are, 0. Let's try this one. This seems all over the place. Turning it up. 23 volts there, and turn it down 19, 18, then jumps to 32 volts. Wow. That'll blow your circuits up. If you had it on a particular voltage and then you tried adjusting it down or up and then it shot up to 32 volts. It's definitely been an interesting time, that. So yeah, looks like there's some notches in this pot. Okay, so let's just keep turning it till we get to the top. So that's 32 volts at the top. If we turn it down, it seems to start to come down and then suddenly jumps back to 32 volts. What if I grab the pot and move it? Yeah, something's wrong with that pot, I think. That 10-turn pot. I keep turning it down. Stuck at 32.6. No, there we are. Look, we've got a bit of a notch in it just there. So I'm not sure where. Let's have a look. Keep coming down until we reach the end stop on the 10-turn pot or 20-turn pot, whatever it is. That's the end stop. Won't go any further, and it's stuck at 32.6 volts, which is bizarre. Okay, right. Well, we've got the DVM set up on DC volts there. So we'll just check channel 1 first to see what the output voltage is coming out of it. Just to verify that there is a current limit to maximum. And then, of course, we'll turn it up to something like 10 volts. Just to see what the accuracy is. And 9.99, there we go, 10 volts. And, well, very good. 80 millivolts off on the DVM, 10.08 volts. Keep going up, see what it is at 20 volts. You can hear the taps getting switched in on the transformer, 20 volts. Again, spot on more or less. and then let's see what it's like when we get to 32 volts. 32 volts, 32.22 volts, so no problem there. We'll test the current on that as well shortly. Okay, we'll just go back onto channel 2, and we'll just link up the DVM onto channel 2's output and just verify that voltage that's displayed there is actually what's coming out. Yes, we've got 32.5 volts there, and if I try and get that to adjust again like we had it, see if we can do that. It's not adjusting at all really, is it? There, nothing. I'm meant to be going up. Here we are, look. So that's 16 volts, and we're getting 16 volts output, so 17 volts, yeah, and then we can just crank it up till 18 volts, and then it shoots up to 32. See if we can get it back down to 18. That's interesting, it's not finding the same position. On the 10-turn pot just moments ago, a few millimeters back in that direction, we had 18 volts. Now we've reached that position and gone past it, and it's not adjusting the voltage. So that's going to be interesting, is that? Is it the potentiometer? 21 volts, so if I can increase it, and then when I try and decrease it, that seems to be working there, yes. It's as if there's like dry spots on the potentiometer. Now I'm going back to where we were, and this area here is roughly where it was. Oh, there we are. So is it the potentiometer or something else, I wonder? Don't know. The voltage though that's reading here is correct with what's on the DVM, so there isn't a regulation problem as such. It seems to be the control itself that's got a defect on it. Now, I can't get any more control out of it. It sort of varies around that point. There we are, it goes up to 32 volts. So we've got like the top end of the 10-turn pot seems to be working, because that's the end stop there going right. We can get some adjustment down to roughly 20 something volts, I think it. Oh, there we are, look. It was roughly about 26 volts. I hope it's playing up now. Right, 26 volts roughly, 27 volts. And that up to the end is fully controllable. So it's like part of a potentiometer is working. But once we get it down to 26 volts roughly, or 27, that's when it goes Pete tongue. So, oh no, 25, and then it jumps to 32, look. Interesting. 25, and then swoosh straight back to 23 now. So it's lying to me, and then it's gone back to 32. I wonder if the potentiometer's got a fault in it, like it's dirty, or it needs taking apart and cleaning maybe. Let's see if we can do that. Definitely something wrong with it, isn't there? Definitely something wrong with it. I keep going down. Nothing at all. Interesting. Right. Okay, right. Before we do anything else, I'm going to check it in track mode to see if it tracks. Because my theory is if there is some digital problem with it, or voltage regulator issue, then when we put it in track mode and we're adjusting channel 1's voltage, it should be able to adjust this voltage. But if there's a digital fault on it, then it would not adjust that, because obviously it's tracking it. Whereas if it's an analog fault, because this potentiometer's got a defect with it, then that voltage will track with this. So let's see if that's the case. So just remove these to a second, and then we get this little jumper lead, put it into track mode. As you can see, the voltage is going down. So basically it's the positive of channel 2, if I can get that on there, to the negative on channel 1, and that then should track. Now if I adjust this, channel 2 should follow it. So that looks to me like it's doing that okay. There we are, we've gone past the point, the threshold where it went funny before, so it's carrying on to track with it. So I would suggest, that suggests to me that it's not a digital fault. That suggests to me that it's more than likely going to be the potentiometer as an analog fault. Because as I say, if it was a digital fault on channel 2, it wouldn't be able to track channel 1's voltage, and it can, so that proves it. So we'll have a look at that potentiometer. I think we'll take it apart, but it seems to be functioning there. Now if I connect up the DVM to what is the combined outputs now, which represents the total voltage of both channels. That's going a bit daft, and it's all over the place as well, isn't it, on there. It's strange that, because that didn't happen until I connected this up. That's going a bit funny. Unless it was this that was just getting seemed a bit strange. Just had a bit of an issue there, didn't it? It started not to track. So is it a digital fault? Seems a bit odd. Because when I connected that negative probe there, that's when this started changing its voltage all by itself. But it's behaving itself now. So I'm not sure if it was that just added intermittent just for a second, or whether there's another fault there, but I can't get it to show itself now. Obviously that won't work while it's in track mode, because it's the voltage here that deals with the track. So I should be able to get 40 volts out now when I get it to 20 volts here on the display. So let's see what the DVM says. Now we're getting 40 volts. And then let's get it right up to 32 volts. We're getting 65 volts there. So if we just turn it down to 32, 64 volts, look. So it seems to be tracking. Could be a dodgy connection, mechanical, electromechanical connection. Could be dry solder joint. It could be that potentiometer stuffed. Maybe it's giving erratic readings to the digital circuitry inside and confusing it. There's all sorts of different things here, but it does look like as if that potentiometer's definitely got an issue anyway. So it's tracking, it's keeping with it all the way down. So let's have a look at that. Right, so we'll remove this link now and get rid of that. We'll go back onto what is channel 2's output, and then we'll take it out of tracking mode. Zoom back to 32 volts. Still no control. Nothing of that ilk until we get nearly to the top of a 10-term pot. There's a few little bits in between, but we can more or less adjust it to 25, and then suddenly it shoots back to 32. There we go. Then we've got a bit more of an adjustable spot there, down to about 20 volts before it shot to back to 32, but it's still a bit erratic. So is it this potentiometer? Right, let's whip the lid off and have a look inside. Okay, a bit of a surprise now inside this one, totally different to the other in many respects. Some similarities, but some differences, major differences. Looking at it, looks like as if the heatsink's obviously totally gone, as we've discussed earlier. I've introduced a fan here, which is constantly on whenever the power supply is on, and there's also some transistors bolted down here. This PCB is different as well. That's a totally different PCB to the one that was in the other. Totally different size, component count. A lot of changes on this one. However, the front board down here looks very similar, if not the same, and it does seem a bit, yeah, I don't know, seems to me like as if maybe they made one for the European or international market, with it having the voltage selection switch here for the transformer, and perhaps they did one for the UK market, which is what we're looking at earlier, because I don't recall that having a voltage selection on it. Not at all happy about something I've just seen either as well. Just here on the transformer, very dodgy. Was expecting better than that. Looks like there's been some wires coming out the transformer that they've not needed, and rather than just bend them back on themselves and put heat shrink caps on and then cable tie them to the loom, which incidentally isn't cable tied on this one or laced up like it was so neatly on the other, but cable tie them to that if you're not in use. But there's a potential, although it's, you know, arguable, that they could, or one of them at least, could touch the case, and that's not what I was expecting to see. You know, that is very dicey, is that. I don't know why they've done that. Let's just zoom in on that and see whether we can see that with a little bit more clarity. So let's just see if we can show you that better. There we are, these two. That's very dicey, very dicey. I would not be happy producing a power supply that had wires just left like that. I mean, that's just ridiculous, is that? And they're not even protected at the end, the bare wires at the end. If they were to come into contact with this chassis, it could cause the transformer to burn out, with ultimately more serious consequences. So yeah, it does seem a bit how you're doing as that one. Insofar as the taps on the transformer, more or less the same with the voltages. We've got a bit more detail here as to the voltages that the transformer supports, and if I can get that glare off, we can see there the different voltage taps. Looks like as if the on the front panel there's a couple of wires that come off here from the transformer, and they supply power to the front board. It looks like as if we've got two voltage regulators here. There's bridge rectifiers, diodes, these four here, which rectify this supply, and then this is an ancillary supply then to supply this board. So it looks like we've got some perhaps voltage reference ICs here that are used as references, and I think there's 7805s, I think, or 08s, something like that. There's definitely a part number on them. I'll confirm that though in a minute. Just have a look at that using my trusty little spyglass, and I'll be able to tell you what it is. Have a look. I've got my little spyglass here, so let me just have a butcher's and see what they are. Let's have a look. Yeah, the 7805s, L7805 CD2 ones, I think they are, and I think it's the same with the other one as well. Yeah, so both of those are 7805 voltage regulators, obviously for supplying the ICs and the voltage reference side. So that's the ancillary supply. We've got the 10-turn pots here again, the same as we did have on the other one. That capacitor is made by Chang, and it looks like it's a 3300 microfarad at 50 volts. Never heard of Chang before, no idea what kind of quality they are, but totally different supply really in many respects. They've also altered the earth look here. Remember on the other one it was fastened to the screw down here that held the heatsink and the back on. They've gone and put a separate bolt through the chassis there, look, to the earth, but yet again they've soldered it, and I don't know why they haven't used a crimped ring connector down there, and it is still Bodget and Scarpa is that one. Not very happy with that, but you know, I suppose it is as it is. You know, I suppose it depends how you look at it. But this potentiometer here, it looks to me, from what I can see, Both sides of the variable resistor, looks like we've got 3 connections, so we've got these two joined together, those two are, and this end one. So it looks like the wiper is possibly the end one, and both sides of the variable resistor are these two. So one end of the wiper, or the wiper, and one end of the variable resistor connected together, and then that obviously is the other side of the variable resistor. So it looks like as if I'm not mistaken, I think there's some screws in it. Am I mistaken? I think might be able to get into them, I think, possibly. Might be able to anyway, I hope so. Not sure how, if I can get those off, but I'll measure its resistance. And what I'll probably do is remove this wire, and then so that the circuit board's not interfering with resistance measurement, and then go across these 2 connections here, or these 3, and check this pot and see what resistance it gives on the multimeter, and that'll be interesting. See if we can get into it. I think there's some screws I can see, unless the rivets just there, look, where my fingernails, where that yellow wire enters. I think there's some screws that hold it together, so we might be able to get into that. I don't know what information it gives us on top. It'll probably be a part number unrecognised that I probably wouldn't be able to get anyway. So we might have to hack it to bits to try and repair that. So yeah, a bit strange, a bit different from what we expected. I'm not sure what revision number in comparison to the other one is. But looks like we've got some more bits on there, on that side as well. Interesting. Ribbon cable. Fan on the back. Strange how this one has a fan in it, the other one doesn't. So, I don't know. Fancy on a postcard with that one as to why that's so different. Perhaps there's some various modifications. Perhaps one's made for the European international market, the other's made for the UK market, I'm not sure. But there just seems to be some differences between them. Anyway, let's see whether we can get this pot off. First of all, I'll unsolder this. We'll do a measurement and just verify that this potentiometer's got a fault on it. It is wobbling actually. I can feel the knob on there moving on its shaft when I move that, so it might not be bolted in very tightly. Okay, so we'll do that next. Okay, so we've set up the DVM now for ohms. So if we connect those together, that's a reading 0.1 ohm. I've desoldered the wire that connected to the end here of the potentiometer. So what we'll do, we'll connect one probe up to this connection here, which is, you know, one side of the variable resistor, and this one here is one side of the variable resistor with a wiper connection, and then we'll just spin it round. It's set to maximum at the moment, and so we're getting, you know, approximately 9 point whatever it is K there, because we're on a 10K scale at the moment. So just set the camera up a bit better. So 9.8 kilo ohms. So what we'll do, we'll adjust. We will adjust the pot downwards to see what happens. So just very carefully. 9.65. So it is falling at the moment as we gently turn it. 9.1k, 9k nearly now, 8.9k, 8.8, 8.7, and then I think it'll start going funny. Oh yeah, look, 9.8k, it jumps to 9.8, there's like a little notch in it just there. If I just turn it up a bit, we're getting that nice adjustment, and then we get to about here, and then bang, it starts to jump up all over the place. Just even touching it here and tapping it, it jumps up to 9.8k again. Keep turning it down. Keep going and going and going. Still staying at 9.8k, and there was a little notch there, it dropped down to 9.2 for a moment, but staying at 9.8. Just keep going, seeing if there's another notch. So don't seem to be changing at the moment, but you never know, it might just start working. And we can't be off the bottom end of the pot now for the minimum setting, so let's just see what it reveals. It's staying at 9.8. Slight difference there just a second ago, but only by a couple hundred ohms, just jumped a bit, but there you are, that's a minimum. So let's get it back to the top again. There we are, a bit of a notch, just felt something as well in the pot. It was like there was a little bit of dirt in the pot that went crunch when I turned it there. 6.2k there, look. And then just keep going up, jumps up to 9.8. So there is a little bit of something there. If I tap the pot and get it to play correctly, tap it again, yeah, 6k, 7k, it's going up. So definitely something wrong with that potentiometer. Definitely something wrong with that potentiometer. Right, let's strip it down, see if we can get that potentiometer out. This 10-turn pot. Remove it and see if we can get into the damn thing. Right, so I think before we do anything getting in it, I think because this front panel's got to come off, I think we're going to have to take this little flexi strip off, I think. Again, fingernails underneath, no prying materials or pointy things or anything like that. Always got to be gentle with those plugs, because if you break that, oh, that's it, it's nightmare. These little lugs break off and then the thing drops apart. You'll try getting that back in, nightmare. So, right, we've got that off. I think it'll be a case of looking at it, removing that screw and the screw on the other side. So we'll do that now. Get rid of that. So let's remove those. Same on the other side. Get rid of that. So that should let the top become unsecure then. Yeah. Then underneath, got these screws here, these three. And then I think when we get the front off, the PCB will become more exposed, so we can then remove the screws on the PCB then to reveal the potentiometer, hopefully. I think it'd be a good idea to pull these knobs off and get the other one off if I can. Got to have hands like Arnold Schwarzenegger to get those off. There's no nuts or anything on the shafts on this side anyway to release, so that's okay. So we'll just turn it back over now onto its bottom, and there's the main switch there, which got some cable on it but not much on it. Let's have a look. So I think, judging by that now, we would best method of attack, because it's the main switch which seems to be limiting it at the moment. I could unscrew the main switch and remove it, but I don't think there's any need for that just yet. So I think it'd be a case of just removing these screws that hold the PCB in. There's one down there. Get rid of that one. There's another one in this top corner here that you might not be able to see very well. And then there's another one in that corner. Just looking out for one in the middle. I spotted a screw in the middle, which is near that little wiring loom that plugs in just there, look. Screw there. So you do get these little secret hidden ones occasionally. And then there's one down there as well. I think that should be the last one, hopefully. Fingers crossed. Not any more screws. Let's see if I can get to that, because it's a bit of a devil to get to. Is that one? Right, so we should be able to remove this just gently. Just be careful that there's nothing hidden that we don't know about. And then we've got the potentiometer, which has got the nut there. It's got that little noise, that wiper noise. Right, so we'll might have to unsolder the bottom connection that goes into the PCB. What we're better off doing is removing that first, that nut, and then desoldering the desoldering that little wire that goes through to this part of the PCB. Now I do have nut spinners somewhere, but you can never find them when you need them, so we'll just use a pair of long nose pliers. It's wobbling a bit there, so we'll just be careful that we don't break anything. Take this nut off as well. Right, so I'm just going to have a look at that lead just under a little magnifying glass that I've got, just to make sure that it's not got a dry joint. It doesn't appear to have. So it's a bit wobbly. I would think it would have more physical strength. So I don't think it's a dry joint issue, but all it does, it just bypasses that first little lug. And just bypasses that first lug and solders to this. They're both the same, but it's just a long wire, that's all. I was just double checking to make sure that there was nothing that stood out like a dry joint. But then we were connecting directly onto the legs with our voltmeter, so therefore, you know, it wouldn't have been that anyway. I would expect that if we were measuring it elsewhere, like on the PCB, and there was a dry joint on that lead. So what we'll do now, we'll just put our soldering iron on there, and then we should be able to just withdraw it then after we desoldered that. Right. Okay. So this is the potentiometer, and it looks like as if we do have some little screws with the look of it, little flat blade screws, flat screws. So we should be able to get those out and perhaps take the damn thing apart and then do it. But you can see what they've done. The wiper, which is on the end here, is soldered to these. So it's just the variable resistor edges there, a wiper on that side. So yeah, we'll have a look at that. No idea if I'm about to buy that part anyway, that particular one. Might be able to buy somewhere from Farnell RS, CPC, a 10 turn, you know, 10k pot, something like that. That'll probably do the job just like anything else. Right, let's see whether we can get the damn thing apart. I'll get me little screwdriver set for watchers. Okay, right, the moment of truth has arrived. If everybody can keep their fingers crossed, we've got 3 flathead screws. We've got the trusty screwdriver. Let's just see whether we can take it apart. Hopefully it won't fly apart, boing, and all its innards go absolutely everywhere, and we forget how it all goes together. So I have to be really careful. Let's see what's inside it. More to the point, can we repair the damn thing once we get in it? Screws aren't too tight, which is good. Not rounded them off or caused any damage. So that's the other thing. Sometimes I put this nut lock compound on and you can't get them off. It bends a screwdriver over and... oh, here we go, look. Right, what's inside then? Let me just get my little magnifier so I can see myself. what's in it. Right, just remove it gradually. So there's some little plastic part there. It's connected to a wire. So we'll just zoom in on that and see if we can give you, the viewer, a better thing. So looks like there's some kind of corkscrew element inside, and it winds its way up, and that's what that's for. That little contact just there makes contact with the variable resistors. It winds up the shaft, and then we've got this connection at the bottom as well. So maybe it just needs a clean. This little finger here, where does that connect to? That goes down to the bottom. So we'll just lay that down till we understand how it works, and then have a little look inside there. So we'll look inside there, and looks like as if there's some resistance material on the outside edges of the that conical shaft, if you like, as you can see. So it must wind its way up. That's how it must work. So I assume then on that, for that to wind its way up, that's fixed, is that? Or is it? No. Let's have a look. How does that work then? Let's have a look. So it just goes there like that. Is this allowed to go up and down? That's allowed to slide up and down then. I see. So this must track in a groove then. That'll track in a groove. I understand now. That wire then allows it to go up and down this shaft. And that little contact there tracks in that little groove there, in those little grooves inside. And it just goes round and round and round, so it goes up and down the shaft there, look. And that's how it works. This contact then, the wire goes through to this, and that has its own connection, which is via these little fingers here. And then that connects down to the bottom. Right down in the bottom there, you can just see there's that ring at the bottom, which that contact there that my thumb's touching makes contact with down there, and that in turn connects to this contact on the end. And the bottom two lugs here and the top two lugs connect to what is this conical resistance material that's running in this spring thing inside there. So that's quite interesting, is that? So it might just need a clean, a bit of a clean. I'm going to see if I can get some better light so we can have a look down that better. Bear with me. Okay, so might be able to see a bit more detail now in there. We can see it's like a spring that makes contact. Now if you look just at the top there with this blue on this terminal strip here, you can just see at the very top of that spring in the middle there's a solder connection. You can just about see that. Not sure how well you can see that. It's just soldered to the top of that spring, and then they'll likewise the one at the bottom there will be soldered to the bottom of the spring, and then you've got the wiper connection at the bottom, which you can see is like a little mark which will need cleaning, and that could be as well one of the issues. But I think the actual issue on this is most likely this finger on there. I don't think it's dirty anyway, because we can see that by that little black mark, but I think the finger needs to be pulled out a little bit so it makes more of a mechanical contact. They look okay, and when we took it out, the enclosure, it was springy and boingy. It lifted itself, so it's not like as if those springs are not taut enough. So I think the issue is probably this finger needs to come out a little bit more, be cleaned, and perhaps be pulled out just a little bit, so it can make contact. Although I'm not sure, might just be tempted to clean it first and then test it, and go inside there and clean that up with a an earbud with some isopropanol alcohol on it. So we'll do that now. And so I've got some isopropanol here, alcohol, and some earbuds, and let's see what we can do. Right, just give it a clean. Okay, so we'll just go around. It's like a metal conical spring, that's all. It's nothing fantastic. I thought it might have been made out of carbon resistance material or something. There's not much dirt on that really. So it's probably just a mechanical contact issue rather than physical dirt or crud that's got in there that's stopping it from working. It's probably just that. But we'll give it a good clean anyway. There's a bit of muck on it, but it's not major. I've seen a lot worse. And now when we look down it, it may be that those black marks in the bottom on that concentric ring have gone. And it looks like they have. There's still a little mark there, but it's nowhere near as bad as it was. Okay. Let's have a look at this and see what this is. Yeah, it does look as if it's a little bit, I wouldn't say it's dirty really badly, but I've seen better days. You might just need prying out a little bit. So we'll see what we've got available to pull that out a little bit. Let's have a look at the selection. Right, I've got a tiny little pokey thing. Is that sort of thing? Oh, no, too big. Let's have a look. Oh, hang on. That might do the trick. Right. Okay, let's have a look. See what we can do. I just want it to pry up just a bit more there. Not going to overdo it because you can break those fingers quite easily and then it'll spring off and that'll be the end of it. So I pried it up a little bit. It's just a little prouder than it was before, nothing major. We've not over egged it, and I'll just give these little fingers a little bit of a clean at the bottom. These, just to make sure they're free of any dirt or crud. Right, I'm happy with that. And I think we just need a bit more isopropanol. We'll get a new cotton bud now, and we'll just clean everything again. Finger grease you want to avoid on any contact surfaces. No matter how clean your hands are, there'll always be some grease there. So just make sure you go over all the connections again with some more isopropanol alcohol. Don't know when you drop it, does it? Got to be careful, don't damage it. Okay, just clean that. And just go in there again, right down the bottom, and just give that a nice wash. Now I hope that the potentiometer works now when we reassemble it. Don't appear to be much dirt on there. That seems okay. Right, we'll reassemble it and just hope for the best. Fingers crossed. Okay, right, now to reassemble it. So I think it doesn't matter what position that is, that spring there. We've got screws to line up. I'm not sure if there's a particular line up on this. Looks to be some kind of a marker there, and I assume that has to line up with something down there maybe. So I think that has to go in line with that blue bit there. I think, could be wrong. So what we'll do, we have to put it in at a bit of an angle as well, like down there like that, and then connect it to there like so. No, maybe not. Just trying to gauge it. There's something, it's got to go in a particular way with the look of it. Like it's keyed somewhere, there's a key on it. Feels that way anyway, could be wrong, might just be me. I'll just move that down, and then connect that down there. What I'm trying to avoid is that moving outwards, you see. I need it to stay where it is on the inside. There, like that. Now it must go together in a particular way. Let's see if I can find it. No, it's not wanting to clip down. It's like there's a, there, that's it. Right, let me see if it turns. Oh, it does turn, though not very well. Seems to have got stuck. Right, I'm happy about that. We'll just take it apart again. This thing here might be a knack to getting it back together. Let's just try it at the top. It's this thing, you see, it keeps coming off. I need it down there. What I don't want is it to start moving. Right, let's try again. Right, gently does it. It's keeps popping off, this thing. I don't know how I'm going to get it to go on. Must be some way of being able to do it. It's got to be. Oh, there we are, look, there. Right, we turn it round then, take it. There we are. It's popped together. Now turn this. No, it's not wanting to turn in a bit, but it's getting stuck. So why is that then? Maybe it's this thing then that keeps moving all the time on that shaft. Right, let's try again. Right. It's getting stuck. It's getting stuck. Don't want to force it, you see, because otherwise it could break it. And that's the last thing I want to do, is break it. So got to figure out how it goes together. Whether it's right at the bottom, it needs to go down here maybe or something for it to make connection. I don't know. Let's put it to about there, I think, and then try again. Let's just see if we can. It seems to come off its thing, you see, and gets pushed up. I don't know. Doesn't seem to want to go back together very well, does it? I think it's got to be at the top or near the top because of this wire that's bending round. Can't go anywhere else, that thing there, so it must mount on it somewhere. Unless as it's going in, I've got to somehow stop it from sort of settling itself in the wrong position. So that's getting stuck again, that's stuck. It gets to there and gets to there and it doesn't go. There must be something that I'm doing wrong. There must be something that I'm doing wrong. It's not wanting to settle in for some reason. There's got to be a way around it. It's got to be. I know that keeps moving. I think if I turn it at the same time as just trying to get it to settle, it might find a groove in that track and then seat itself. But it's definitely not playing ball. There must be a knack to getting these to go back in. See, now it's not even finding that groove. It's not even settling in. It's getting all tangled up. So, I don't know. Let's try this then. Because what happens is when you hit that wire, it moves to one side, you see. And I don't want it moving to one side. I want it to stay where it is. Must be a way, must be a way. Let me see if I can figure something out and then try again. Right, after a lot of faffing about, I managed to get it back in. It was just getting it started, that's all. You have to get as you put this top bit back on, you have to just gently start winding the shaft. So that little finger on that plastic holder starts to rotate and find its way into the groove. And then you've got to spin this this blue top round to get the keyhole to lock in, and then you're away. And now we're just putting the screws back in. And I've already, before switching the camera on again, just turned the shaft, and you can hear the fine sort of indentations that's on the slider as it's been rotated round. It makes quite a unique feeling. It's like a potentiometer that's got a notch in it. That's all I can describe it as. It's like a notch inside the potentiometer, and there's thousands of these little tiny indents within the notch. That's all I can describe it as. But we'll see whether that's repaired it. Hopefully not have to go back in it again. And I just need to measure it on the multimeter before we reassemble it back into the unit. And it's just trying to get these damn screws back in. They're so tiny. It's just unbelievable. And back with you shortly. Okay, so got the thing assembled again. Just connect these crock lids up to the multimeter and start to turn this. So we've got it at the end stop now, which is the maximum position, 9.8 kilo ohms, and we'll just start to turn it down. See if we get any erraticness. So 8k, and then 7k, seems to be smooth so far. 6k, 5k, 4k, 3k, 2k, and then 1k, and then we're down into the hundreds of ohms now, down 7, 6, 5, 4, 3, 2, 100 ohms range, and then into the sub 150 ohms, and then down to almost 0.5 of an ohm there. So seems good. Just keep going up. Obviously the meter's trying to track it, so that's 340 odd ohms, 500, 600, 700, 800 coming up, 900 ohms, 1k, 1.2k, right the way up to 1.4, 5, 6, 7, 8, 9, 2k. Again, going through watching the 100 ohm ranges past the decimal point to make sure they're not jumping up and down as well. 3k, and then 4k coming up very shortly. Seems to be turning nicely freely as well on the shaft. 5k, 6k coming up, nearly 7k, and then get right the way up to what is 8k, and then 8.9 I think it went up to roughly, or 9k, and then there 9.850k. So we won't go any further now, it's at its end stop. So I think we've repaired it. We're very, very fortunate, you know, that we could do that, because most potentiometers that I come across these days are riveted here, and they've got rounded tops on them as well. You try getting them out. I mean, I've broken loads of potentiometers over the years, especially on the Sony receivers and things, where they have you press the shaft in as an on-off switch, you pull the knob out and turn it for squelch control, let go of it so it pops back in, and turn it then for volume. So it's like 3 or 4 sections to the potentiometer, and they're riveted at the bottom and riveted at the top. And I've actually got them under sort of a bench drill, drilled out the rivets and then got into them, and they've been a nightmare to repair. A lot of them have failed at repairing, you know, in the past. So that's testament really to the quality and the manufacturer who's made those, that they're actually screwed together, not riveted, so we can gain access to the thing. What I did notice about it as well, which is quite unusual, a lot of potentiometers, particularly 10-turn pots and non-10-turn pots, they have like a grease, an electrical compound, a grease inside, like switch, like the type of thing that a switch cleaner would emanate when we're using that. This didn't have any of that inside. It was grease free. Obviously it's got a resistance spring going all the way down, and there didn't seem to be any of that electrical grease put inside to keep it lubricated, which I'm surprised at, because quite a lot of potentiometers have got that grease in them. But may not be a need for it on this, I don't know. But anyway, at least we've repaired it. I've held the thing up to the microphone, might be able to hear it a bit better, the actual indents within the potentiometer if you listen. Might be able to hear that. Don't know if you can hear that on camera, but I can hear it, and I can feel it through the shaft as well as I'm turning it. It's like thousands and thousands of tiny little indentations in the way that when it moves. It's quite weird. But anyway, we'll put it back in the power supply, put everything back together and give it a test. Back shortly. Right, let's see if we can reassemble it then. So, plug that into there. We've got that little wire to attach. Mustn't forget about that. Get the washer and nut. Reattach it. Just got to be careful as well that you don't dislodge these LEDs, because you've got to line up these little holes. So if you move them over, then try and put it all back together, then when you look at the front, one of the LEDs, you can't see it poking through the hole. So just got to make sure that you've not pushed them. Obviously these are not shift, these are 7-segment LED displays, but just put that on. Just make sure that doesn't start spinning around at the back, because we don't want the contacts facing up, we want them facing down for the connections for the wires. Just tighten that up using our pair of trusty long nose pliers. We don't need to be too tight, we're not Arnold Schwarzenegger. We just got to make sure that you know, it's tight enough and it won't swivel round, and thus Should really use a nut spinner, but trouble is you could put too much torque on my nut spinner and end up breaking them. So that's more than tight enough, that. Okay, so we'll solder the wires back before we forget, because when it's back in this section here, we won't be able to get the soldering iron to it, so we'll just bend that over there. We've got this little yellow wire there as well, which probably better going that way. And then soldering onto those two there. So we'll just get the soldering iron and give it a solder. Oh, where's my solder gone? It's vanished. Every time you need it, it's gone. Where is it? I had it a moment ago. It can't have gone that far, surely. So, anyway, I can't see the woods for the trees sometimes. Right, let's have a look here. Okay. Let's see if we can that's soldered quite nicely. Might be able to see if I can get it through one of those holes. I'm not sure if it will though. Might be a bit messy, that. Might be as well. I can get that through that hole. There. Then we can solder it both there and there. So that'd be quite useful if we could do that. And then same at the top here as well. So essentially we're connecting these two together, you see. Just check that, make sure that it's decent soldering and not a bodge job. Yeah. We've still got that connection broken on this top land there, so I just need to apply more solder and get those two to touch one another. So let's just double check that, see what we can do. It's got stuck. That's it. So they're connected together. That's all we need. And that way then electrically this wire is connected to the bottom connection as well as the top. This wire at the bottom here is nicely soldered and connected to this terminal there. So that's all ready to rock and roll. We just got to make sure now that the LEDs haven't been moved or dislodged when we push the circuit board forward, because obviously that'll stuff the final test when we saw the LEDs are nicely lined up, they're not being squished or moved around. So what we need to do now is gently reintroduce the PCB back into its locating holes, and then we need to just double check that the LEDs are visible through those little tiny holes at the front, and they are. I can just see the reds of them. Okay, right, now that we've established that, keep his fingers on it so the board doesn't come out and go back in again with the LEDs dislodged, and then we'll get the first screw in. So we'll put that in there instead. Start that one off in the middle, that way that it can't come apart, you know. and stop it from dropping to bits. There we are. Just tighten it up. Careful not to put it in cross-threaded or over tighten it, because it is going into plastic after all, you know, so it's not got to be torqued up too tightly. Just be careful this screw doesn't crush that black wire under it. Just make sure that that's out of the way as well. That's it. Next screw. These are like self-tappers, that's all. They're not metal machine screws or anything like that. And I see that hole. Oh, it's there, look. Difficult to see from this angle. There we are. Come on, there we go. Right. Always keeping your eye out as well when you're doing this for any strain on these wires, because sometimes when you're putting things back together the wires can pop off, and then, you know, when you get it back together and try and test it, then there's nothing there, it doesn't work, or it bursts into flames or something like that because one of the wires has come off and short-circuited on the chassis casing, or touched a component on a board that's not meant to, and then that's it, then you end up getting into bother. Right, I think this is the last screw then down in the bottom right hand corner. If I remember rightly, this was a bit of an awkward devil, was this one, I think. Rightly, yes, I think it was just down there, wasn't it? And we'll reconnect the ribbon cable once we've got the front nicely fastened. It wouldn't be recommended to reconnect the ribbon cable until we've got all the screws in place, otherwise you risk tearing the ribbon cable or damaging the connector. So, but just having a final check, make sure the wires for the switch haven't come off, none of the cables that connect to the PCB have come off or anything like that. Everything seems okay. Binding posts and everything are all okay. There's a diode across the binding posts as well that you can probably see down there as well, and another one on that binding post, a diode that's hidden there. So they look okay. Those capacitors look as if they're fine, and just make sure all the wires are out the way and we reintroduce it. So this goes underneath the metal chassis, if I remember rightly, and just position it appropriately. And I can't remember now if that goes, oh, that goes on the inside there, so that's it. Right, so these are the machine screws. So these obviously need to go in countersunk machine screws. Turn it round the other way. Line it up. That's that. We'll turn it over. And just 3 screws here. Now these underneath, I've got these little washers on them. So it's good to remember what screws went where, and put it in the middle. See if we can get that one started first. Although I made a mess of it already. Let's try again. Is it going to play a ball? There we are. Just getting it lined up. Once you've got it lined up and started, sometimes you have to leave that one slack and then the others will line up as well, because if you tighten one up then you can't get the other 2 in. That's something that happens quite a lot, but maybe it'll leave me alone today, that bit of bad luck. Right, get the last one in, then we're ready to connect that flexi strip. All being well, it'll turn on and work after that. Right, so that's okay. Now then, the flexi strip, again, always be very, very careful with these and not to overdo it trying to get these in off or on, and make sure that you get them seated properly. And if I just have a look here, they've got a habit of closing of these little gates when you try and push this in, so just got to keep an eye on that little just get it going. Steady away, no rush, take it easy, wiggle it up and down a little bit, and then we're ready then just to close these gates on there. So when we think it's in and it's not diagonal, and then just fingernails only, press in both sides of the connector there, get that to close. And then the last check is to make sure that this blue line is straight in comparison to the connector. If it's at an angle, if it's like that or that, then you know it means that the pins inside haven't lined up, they'll be like that. So make sure they're straight. So that blue line has got to be perpendicular to the connector, otherwise you know it's got to be correct, otherwise you're going to end up like that and shorts and problems. And it chews up the tracks on the foil, so when you take it apart then you have one bent back like that on the ribbon, and then you've messed it up. So yeah, you've got to be really careful with these. I'm happy with that. That seems to be okay. You can give it a little tug outwards just to make sure it's home, but that's fine. And now we're ready to power it up. But before we do that, as we should always do with any piece of electronic equipment we've worked on, we just need to briefly look inside and just run a size over everything just to make sure no wires have pinged off and touching, or there's something trapped or something not right. Just to make sure that the main switch indeed itself is okay. I think we can do that by looking at it there. These wires are okay there, they're not exposed or anything. And make sure that the LEDs on the front are visible so they're not hidden behind the plastic panel. And then we're ready to reattach the knobs. Now I don't think the knobs are anything special. I don't think there was a particular knob for a particular potentiometer, but you never know, might be different size shafts and things like that, who knows. There's no markers on them that have to be lined up, so that's good. You just push them on and then that's it, job's a good one. Sometimes if they've got markers on them, you have to turn them to minimum or max positions and then line the markers up with them. That does seem a bit slack, that. I'm not happy about that. Let's just see if it goes on this. That's better. And that there. Right, so that's that. Right, okay, so we're going to power it up now. We've done his final checks and everything. Should be okay, good to go. So let's get our trusty power lead, connect it up. Okay, we're connecting mains. We've got the covers off, so you know shouldn't be touching inside any live parts or anything like that. Just make sure it's switched off there. Okay, right, so we'll turn it on and let's see what we can measure. Just move that to one side a little bit. Okay. Right. There we go, look. Our voltage can be adjusted nicely. It's going down. That's working, so we're okay, we're good to go. Turn it to 10 volts. Okay, so let's put the voltmeter back onto what is volts DC, and press it there because it's about 15 feet away from me. There we go. And connect the output up. Okay, so what we're reading then? 9.972 volts. Here's damn it, and 10 volt range, so that's good. And we'll just turn up the voltage now to something like 13.8 volts. Yeah, 13.8 volts. 20 volts. Let's measure that. 20 volts. Very nice. 25 volts. 24.9, and then right up to 32 volts. 32. It's there, no problem at all. We did look at this one earlier as well. We'll measure the current as well, and that's 6.8 volts, so 6.97 volts there. What's this? We'll put it to 10 volts. 10.1 volts, so here is damn it. Okay, so we can have a look at the current on both now. So let's move over this lead here to current. Just bear me a second. Put that onto the current setting on the meter, and then I have to put it onto the current DC setting, and at the moment it's on the where is it now? Range. Can't remember where it was. Amps. Milliamps. 10 amp range. There we go. Right. So should be able to turn this up to 500 milliamps thereabouts. And of course we're getting 500 milliamps, and then 1 amp. Yeah, 1 amp. 2 amps, we'll go straight up to 2 amps, then 3 amps. That's 2 amps there, look. Again, dBm, clarifying that. And then turn it to 3 amps. 3 amps. Nothing wrong with that. Okay, over to channel 2, which was a channel that wasn't working properly. Connect up the current meter to that. And then we'll turn the current up now. So again, get it up to 500 milliamps. About 500 milliamps roughly. A bit finer on that one to adjust. Come on. It wants to either go to 49 or 51 rather than 50. There we are. 500 milliamps. Here's damn it on the meter. Right, let's try 1 amp then. 1 amp on the meter, and then go up to 2 amps. 2 amps just under, and then let's crank it up to 3 amps. 3 amps. So there we go. Right, next thing we'll do is we'll just check the track function. Okay, so in the track mode then we should get the both channels to work together. So we'll put it into track mode. We'll get our jumper lead and connect it from the positive on channel 2 to the negative on channel 1. So that's that. Okay, so they're both tracking each other now, and then we should be able to, you know, wind it down and The relay is going for the taps. That's tracking nicely. Yeah, that's okay. Run it up. And then to 30 volts we'll call it. So what I'll do is I'll adjust it to 30 volts and then we'll just check now the output to make sure there's 60 volts DC on the voltmeter. Obviously I've changed the current lead round into the voltage port on the meter, otherwise you'll end up shorting it out. So that's always a good thing to check. Okay, so there we go, 61 volts, which is the 0.4, 0.7 added together. If I turn that up to 32 volts then, and then we've got 64.53 volts. So there's nothing wrong with that, you know, it's tracking nicely. There's no issues there at all. Wonderful. I'm very pleased with that. Very pleased indeed. Wonderful. It's all back together now. All repaired, all done. So I'm very happy with the repair. I think it's been quite an interesting time doing this repair, especially being able to take the potentiometer apart. One thing that I did forget to mention in the earlier part of the video when we're repairing the potentiometer is the fact that the little black wire which went through the spindle, there was a blue spindle, had a hole drilled in it, and the black wire from the finger contact that goes round the swirl in the outer shell, which is the resistance wire, that has a connection of wire which we saw. That little black wire goes through the spindle, there's a hole drilled in it, you see, tiny little hole, and then it curls round in like a swirl and then solders then to the contact at the bottom of the spindle, which then went to those fingers, if you remember, that turned at the bottom. Now that broke off actually. Now I'm not sure if that was part of the original fault or whether it was something I introduced by manhandling it a bit, but anyway I had to solder that back on. It was quite easy to do, I just dabbed a bit of solder on it, got it back on, but it was something that I noticed and put it back together, and it was a devil to get back in. You've got to sort of seat it properly, start it turning so that it finds a groove within that spiral coil, if you like, of resistance material, so that the contact can make connection then and find its groove, a bit like a record player V groove and the record player needle having to try and locate its groove when you're playing a record. It's the same with this. You've got to start that spindle off. If it gets stuck though, best not to force it because you'll break it and chew it up. So you know, if it gets stuck, start again, be patient and just keep turning very calmly and very gently until it seats and starts to go with it. But yes, a bit tricky getting that back together, but I'm sure if you have patience it's easily done. But yeah, great little power supply, superb little unit. I couldn't find any circuit diagrams for it online. I looked all over. The schematic diagram, it doesn't seem to be available, although I did manage to find, I'm not sure if I've got it still on my computer, just press escape here. I did manage to find an instruction manual for it, but the manual's sort of written in sort of Chinese English. It's quite poor, but that's the manual there. Now I'm not really sure if you can see that very well on the on here, but it's typically the sort of thing that you tend to find online on these websites that do your copy manuals and things. It seems a bit silly, the description. It says has master slave tracking, constant voltage, constant current, which I understand. The main outputs can be connected in parallel or series, which I understand. Then it says voltage regulator on its own. Why they put that in, I don't know. Steady flow automatically converted. No idea what the hell that means. Steady flow automatically converted. Well, anybody's guessed that one. The state will not use any external damage. No idea what that means either, but anybody's guess yet again. Just you think that they'll find somebody who knows English well in order to write these manuals. Anyway, it says here that it's got a triple output, but it doesn't unless, of course, this blanking plate here has got terminals in it. Series of parallel operation, current limitation, auto switching between voltage and current operation, and then we've got a specification here as to channel 1, channel 2's voltage, current, overload effect, ripple and noise, regulation, manual effect, mutual effect is it, tracking error, and indication method. Reliability, mean time between failure is upwards of 2,000 hours. General characteristics as well, white and grey colour. You can buy it in 2 different colours. It weighs 4 kilogram. It's got a power cord. So it looks like it's sold by these companies here. So we've got Element 14, Farnell, Newark.com, CPC, UK, and then what's that? momelectronics.com. So they sell them as well. So yeah, quite a nice little project, and I think that's it. We've come to the end of the video. So if you like the video, please subscribe and give it a thumbs up. It helps the channel, and we'll see you again in the next one. So thanks ever so much for watching. Take care. Bye bye.